Okay, so last time we finished point-to-point communication, and so this week we're going to start into collective communication. I think the website's working now. It was completely down yesterday for most of yesterday, so I had some problems. Okay, so we did the trapezoid rule last time, and one of the things that we did when we wanted to communicate um, the we wanted to communicate the calculations of the integral on those intervals, we used the sends and receives to communicate between the processes. But communication in any parallel program is always going to be the most expensive operation that you use, just because. So communicating between a processor and its cache, for example, is the fastest memory operation around. But and then um, between memory and your processor, it's still the fastest. But communicating between one process on one particular node with a computer, another node that might be, at the other end of the room, in a large room that would contain one of these cluster computers, is going to be a very expensive operation. And so when we're in the trapezoid rule, when every process is taking its turn to send its information to the root node, we're losing a lot of time that way. I want to demonstrate real quickly why thinking like this is the wrong way to go. It's more of we're not really thinking parallel yet. So let me skip ahead and just show an example. Okay, so each process is sitting there idle while it's waiting to send its information. But there's a more efficient pattern or a more efficient structure for communication, and this is one particular structure that we'll show is this tree-structured communication. This way this increases your the efficiency, your use of all the processes, and it can reduce your time. So if you say each process will take its turn sending its process, if you have n processes, we could say that's n time. Well, using tree-structured communication, like this one here, can reduce that to something like log n. And so let me illustrate that idea with you. Let me talk through this picture. Okay, so in the trapezoid rule, we have 8 processes, like those shown here. Each of these 8 processes calculates the estimate of the integral on its own segment of the interval and returns a number. So say these numbers are these x's from 0 to 7. Well, before, what was happening is each of these processes was sending to the root node one by one. So this would send to the root node 2, 4, and 8 of these would each take their turn. Well, in tree-structured communication, each process will have its own information, but it works by something like this. So say process 0 would send its information to process 1. Process 2 would send to 3, 4 to 5, 6 to 7. And all that would be happening simultaneously. So we could say, well, that only took 1 time slot. So process 1 receives from process 0, and then it sums up those two numbers. 3 receives from 2, and it sums the 2, and so on and so on. So now we see process 0 still has its own number, but now process 1 has the sum of the 2. Process 3 has the sum of these two, and process 2 keeps its own, and so on. And then we do the same thing are sort of the same thing. Process 1 will send to process 3, process 5 will send to process 7. And then in the next time step, process 3 will send to process 7. So if you notice by the end, you can see that process 7, in the end, ends up with the sum of all of these. Yet if operations were time steps, it only took 1, 2, 3 steps. Compared to in our implementation, where each process sends its information one by one, it took at least 7 sends. So that's less than half. That's less than half the time. So two reasons why our first implementation of the trapezoid rule was bad, using just the sends and receives, is that process 0 was doing all the work in the sense that process 0 was the only process handling all of the communication, or the only process handling the communication. And also process 0 was the process that was adding up all of the numbers. And so process 0 was doing a ton more work than all of the other processes. And again, your algorithm is only going to be as fast as the slowest process. In this case, it was process 0. So to speed up our trapezoid rule problem, we want to implement something like this. So to generalize something like this to a lot of processes, to any number of processes that we want, to make that arbitrary can be sort of difficult. There are a couple different schemes that we could think of to implement some kind of efficient communication like this. There are different patterns that we could use. But that's all going to be kind of difficult. Fortunately, MPI has functions that handle all sorts of collective communication, we call it, all sorts of collective communication, and does it all under the hood. One of the MPI is going to ping your system and try to find the fastest connections between each of the processes, and so it'll use the specific communication structure that will be fastest for your system. And so to implement something like this, all that we would need to do in our trapezoid rule algorithm is to change our communication structure to use what is called a reduce. The function that we're going to be talking about is reduce, and that's when we took all of these processes and we reduced it to one number. So let's just quickly show the syntax for reduce. So this is the reduce. Here, what you're going to send, what you're going to receive. Here you specify the operation that you want to use, which are MPI predefined constants. So for the trapezoid rule, we'd want to use something like sum, though there are others available, and I'll list them here. And then we want to specify the root where we're gathering, or where we're reducing all of those to. And so now let's demonstrate how to do that in the trapezoid rule. First, I want to pull up the code for the previous one so we can compare them. Okay. So in the last one, the communication was, if you're a process 0, you have your integral, and then you're running through a for loop to receive from each of the other processes. And if you're not process 0, you're sending your information. Well, one of the great things about collective communication is it simplifies this all into just one call. So all of this suddenly turns into this, and we can do it a lot faster. So this is just the same as the previous code. We went through, called everything command line, calculated our intervals, defined our integrate range function, and then when it got to the communication part, we just reduce the integral and save it into something like total, sum them up and sum them to the root node, and then the root node will save that. So let's run that real quick. And it works just the same way. Okay. So this is the first collective communication function that we've covered. Now we're going to go through a few more. So the first that we talked about was reduce, and it implemented something like this tree structure where it took all these numbers and it used some kind of operation. We used a sum, but we can use a product or max or different logical operators and reduce them to 1. AllReduce is similar. AllReduce, instead of taking all of these numbers and reducing them to 1 point, we'll take all of them and it'll reduce it to 1 point, but each process will also have the value for that. And it's kind of cool the way that it implements that, because it uses, and I don't have a good picture of it yet, but it implements kind of a butterfly type structure, where this reduce, as you can see, it kind of, it's this tree that leads to this point. But you notice there's a lot of these processes that aren't doing anything after the first few operations. Well, an AllReduce is like performing a reduce where, so this process 7 was the root node. An AllReduce would implement a reduce, but it would use each root, or it would use each process as the root simultaneously. So it would reduce to this one, but at the same time, these other processes that are unused would do the same thing. They'd be sending to these other unused processes. And the AllReduce is almost going to be the same speed as the reduce, because these processes that are unused, they can they fit into each other. They're about the same speed in theory. In practice, the AllReduce is a little slower. Sometimes it's important. You would use use the AllReduce only when it's important that every process has the reduced value. Again, here are different operations that you can use. So now we're going to illustrate two more, broadcast and scatter. And we're going to introduce a new algorithm, or just a new computation. So let's look at just calculating a dot product. We'll just be calculating the simple Euclidean dot product of two vectors. How would you, if you have two vectors, you want to compute the dot product by multiplying the elements of each vector one-to-one with the corresponding vector. What would be the best way to, or what would be the best way to parallelize that? Just a review of concept. If you could do anything, how would you imagine parallelizing the dot product operation? Yeah. Yeah. So just segment the vector into blocks, and then each process will calculate the dot product between those blocks. And then you'd get the value, and then you would just reduce them. Yeah. Okay. So now we just need the tools. How do we segment up that? How do we segment up those vectors? Well, here we're going to assume that the vectors that we want to take the dot product of live on one of the processes. We'll say that they only exist on process 0. So we need to communicate that information from process 0 of those vectors to all of the other processes. So the way that we do that is with scatter. Scatter is going to take a vector, and it's going to divide it up. It's going to take data from one process, like a vector, and it's going to divide it up and send it to all the other processors in the communicator that we're using. Scatter, just to know, if we're dividing up that vector, then the size of the communicator, the number of processors there, has to evenly divide the size of the data, the size of those vectors. There's another function that we can use when that isn't the case. That would be scatter b, and we'll talk about that later. But first, we'll go through the code for parallelizing the dot product. But let's take a break first. Okay. So back to the collective communication. Okay, so we wanted to parallelize the dot product. We were going to take the vectors and we wanted to break them up into small parts and then send those parts to different processes. Each of those processes was going to take a chunk of the vector. And if you just have two segments of vectors, you can take the dot product of those two, and you'll get a singular result. And then if you just sum all the results from all the processes back to one value, you'll have the dot product of the whole vector. So let's look at the code for that. Okay. So I've set the code up in this example. You can just input any. You can input the size of. You can input the size of the vector that you'd wish to compute, as well as the number of processes. And then for the vectors that I'm going to be computing, they're going to be just evenly spaced between just numbers that I just chose arbitrarily. So I'm reading from the command line how long I want the vectors to be, and then I'm using linspace and putting those in here. So they'll be evenly spaced between these numbers. And again, we're assuming that that these vectors only live on the root node, and that's plausible because, like we talked about, if we're reading from data, typically without some of these more advanced technologies, we're just reading from memory in one stream, and so we're going to be doing that with the root process. So we're assuming we read in this data from some stream, and we read it into process 0. I should change this. I was trying to avoid this, but this this rank here is being treated as an attribute of the communicator, which we can do in the object-oriented way of MPI or mpi4py. But I've till now I've been trying to mimic the way that you would program this in C, and so you wouldn't have attributes like this, and so I'd have to save it into rank. I'll change that, but just so you know that you could write it that way, this is how you could do it. So that saving the vectors only on the root node. So we have to initialize our variables as NumPy objects. I'm going to run a quick test for conformability. So I want to make sure rank 0 is going to do that. So we want to this is just to make sure that the x and y are the same vector length, but that's a little extraneous because I have them equal to each other anyway. And then I want to check to see that the size of those vectors can be evenly divided by the number of processes, because for the time being, we're not able to handle the case where they don't. You saw this earlier, we're just using comma bore in the case of an error, so that will kill all the processes. And then we want to know the size of each of these chunks, the length of each of those vectors. So n is the vector length divided by the number of processes, and that's going to be local n, which is the local length of the vector. So we want to just quickly broadcast local n to all of the processes. Yeah, okay, I haven't talked about broadcast yet. So let's, yeah, good question. Okay, so this is the picture for reduced. We sent and they summed them up. Well, broadcast is just the opposite. Broadcast is if one process has some information, it wants to send that information to everybody else. So normally, or in the last chapter, we would have done that with sends and receives, and so one process would have sent one by one to everybody. But instead, we can do that faster if first this process sends to this one, and then in the next step, that process sends to this process sends to this, and then in the next step. So this is a little more collective. So it's just the same thing as sending and receiving to everybody. Okay, so we broadcast from process 0, we broadcast the value local n. So everybody calls local n, every process calls local n, but the value of local n at the root is the root process is going to have the relevant value of local n, and then in all the other processes, local n, whatever it is going to be overwritten by the one on the root process. So now each process knows how long of a vector to expect, and so we initialize the NumPy arrays for the local x and the local y vectors. And now they know how much memory to allocate for each of those vectors. And I suppose you could have calculated this on each process, but we're assuming that only the root node had the information about the size of the vectors and the vectors themselves, and so all the other processes had no idea. And I think mpi4py with NumPy objects, for the most part, it has built-in NumPy object discovery in there. So normally when you're using these functions and you put in an object, you'd have to specify this is an integer or this is a float. But when you use NumPy objects, it can figure it out on its own. And that's just something that's specific to mpi4py and NumPy objects. If you wanted to do the pickled method, or if you didn't want, if you don't want to use NumPy objects, but you want to use these uppercase communication functions, you have to specify when you send this is a float 32 or whatever. But this just makes it a lot easier to just work entirely in NumPy objects. So each process initializes the vectors, and then here is where we divide them up. We use scatter. And so scatter works in almost the same way as broadcast. It's going to do something similar where, the root process has all of the whole vector, and then it just starts splitting them up, and it does so in a collective fashion, just similar to this one. And so we're scattering x from the send buffer, and we're receiving it into local x. So local x is going to be a lot smaller of size of vector than x, and we're scattering from process 0, and then we do the same thing for the y vector. And so now each process is going to have something at the something in local x and local y, and then so now that each process has its chunk of the array, then each process is just going to call the NumPy dot product function, and it'll take the dot product of local x and local y and save it into an array, which I may not have needed to do. And so we save the result into local dot, and then we need to sum them all together from all the processes. And so we use AllReduce. We're sending local dot, and we're going to save it into our sum. We'll call it dot, and we'll use the sum function. And so now the default value is that we're reducing to rank 0. So we're going to print the value that rank 0 has, or rank 0 is going to print the value that it computed in parallel. And then because computing a dot product won't take really any effort at all, we'll compute it the same thing in serial just to verify that we have the correct answer. So let's just run that code real quick. This is the same code. it. The vector's 10,000 long. And so in parallel, we compute this, and we can see that our answer was correct. Let me run an example just to illustrate the scatter. So this is okay. So this example. On the root process, we create a vector to divide. Here I've written it to ensure that no matter what, the size of the vector will be divisible by the number of processes that we have. When we run the scatter, because all of the processes will call scatter, it has to have at least something. It has to have x at least initialized when we call it here. So all the other processes are going to initialize x, but it will give it none. Then we're going to initialize the receive buffer x local to be just the length that we've specified here. And so we'll save into that, and it'll come from process 0, and then we'll just print all the values that the processes have for x and x local. Okay, so process 0 for x has this this long vector here. Processes 1 and 2 have nothing for that same thing, and then you can see after the scatter, x local process 0 ends up with just a third of the original vector, another third, and another third, and they're in order 1 to 3, 4 to 6, and 7 to 9. So we mentioned how in our dot product code, we mentioned how we can only that the size or the number of processes has to evenly divide the size of the vector, or else the scatter isn't going to work. And so in the case when that when we want to program it so that we can take in, any number of or any size of vector for any number of processes, we have to use the functions scatter v and gather v. Scatter v and gather v. So I put the syntax for that at the bottom here, and it's a little more complicated, but not too much. So scatter v the way it's going to work is that you specify exactly how you want it to break up the vector. Before, it just, because it divided evenly, it just scattered them, divided them up into even or to uniformly spaced chunks. This time, we have to, first, we have the send buffer. So whatever the value is of the sending variable, we just put in the sending variable there. And then this tuple of integers that we call send counts, that refers to how many elements we're going to give to each process. So this is a tuple, and the length of the tuple is equal to the number of processes. So if there's 3 processes, and we wanted to give 1 element to the first, then 2 to the second, and then like 9 to the third, then it would just be a tuple of 1, 2, and 9. And then tuple int displacements, that refers to how many, when we're scattering, we have to specify where we're breaking up each vector. And so this would be the displacements from the first element, the referencing element in the vector. So how many, the displacement from the place we wish to start. From the place we wish to start the new vector from the beginning of the original vector. So what I mean is, if I had the vector 0, 1, 2, and I wanted to split this up into something that would give a 0, 1, 2, 3, and then 4, 5, 6, 7, 8, 9. If I wanted to split it up into 3 vectors, then the displacements on this would be a tuple where the first one, 0, we'll just put a 0 because it's not displaced from the first at all. But then the second vector, we want it to start at 1, so it's displaced by 1. And then we want the third vector to start at 4, so it's displaced 1, 2, 3, 4. And then the send counts that we talked about just now, that would be, we want to send 1 to the first, 3 to the next, and then 6 to the last. That's how those work. And this allows for a lot of generality. Because if we wanted to scatter, but we didn't want to send the whole vector, we wanted maybe to skip over a few and only take chunks out of the vector, then we could use the displacements and send counts to do that. Also, this is important for the C version because in C there's no vector length discovery, and so you always need to specify how long the vectors are, and that's a big reason for why it's set up this way. Right. Okay. So after the scatter, how can we pull them back together? Okay. I did not give the syntax for gather, and I'll add that in. Yeah. For gather, gather v. There's also just the normal gather, which is just the inverse of scatter. It's just about the same as the scatter, just reverse them. With the gather v, it's about the same thing. So here, each process is going to be sending its chunk, and then when we're receiving it, we just have to specify where we're going to receive it, and then the same thing, how much we're receiving from each process, and then when we're storing it into the vector, how do we want to store it? How many, when we insert this chunk into the main vector, where do we want to start? So we give it the displacements and where we want to start it writing to memory. And then the last thing, which is in both of them, is the data type. And here we do have to specify the data type. So the data type that we'll usually be using is mpi double, or you might use mpi int integer. Here's an example of scatter v and gather v. I just create a vector here, then I scatter them to 3 processes. I give 1, 1, and 9 these displacements. And then I undo what I did by gathering them back together. So just to talk about these are going to be important for the exercises at the bottom. So the first exercise is going to take the parallel dot product, and we want to generalize it so that it can take in any number or any size of vector and any number of processes. For your assignment, you can assume that there are, just for a little convenience, you can assume that the size of the vector is greater than the number of processes, just so you don't have to worry about that. But that you would just use scatter v, and then you would just reduce them. And scatter v, you could do that pretty easily. Remember to load balance, so a whole bunch of those, they're just going to have one more than the rest. Another assignment is we're going to implement, we're going to parallelize the operation of multiplying a matrix by a vector. There's 2 ways to do that. The assignment is going to have you come up with the 2 ways of doing that, and then you're going to talk about which one would be better. And I give you, they use different operations. I talk about how they both use scatter because both distribute the matrix. One is going to distribute them as if the matrix were in column major order and the other in row major order. But one is going to use a broadcast and a gather, and the other is going to use a scatter and a reduce on the vector. And so that will be kind of interesting to come up with that. Here I have some example code of how to scatter a matrix, or just demonstrating scattering a matrix. And this involves, say you had a 3 by 3 matrix. This is going to scatter that to 3 processes. And so here, for this one, you can just assume that you can even just assume that the number of processes is always equal to the number of rows or columns in this square matrix. One important thing to talk about in terms of why collective communication is so important. Here I have this hypothetical situation of comparing the serial code to point-to-point communication and collective communication in the dot product computation that we use, the dot product algorithm. So here I'm going to hypothetically assume that all of these operations take the same amount of time. So if we were to analyze how long these would take, first I look at the serial code, and I see that the serial code doesn't have to broadcast anything, it doesn't have to scatter anything, but it does have to compute the sum, so it has to multiply out all the things and then sum them up, and we'll say, well, for each element of the matrix, let's say that's 1,000 operations. We can say I'm kind of compounding a few operations into one, but that would take about a total of 1,000. Well, if we were to use point-to-point communication to implement that broadcast, say we had as many processes as we had elements of the vector, which would be terribly inefficient anyway, we would have to send one by one 1,000 times, scatter one by one 1,000 times, scatter 1,000 times, and then if each process only had one element, then it would only have to compute one multiplication and sum. And then when we reduce the result, those results would have to be sent to the root node one by one. And so the total number of operations in this hypothetical situation would be 4 times the size of the serial code. And so we can see here that in some cases, using point-to-point operation or point-to-point communication, we can end up, our algorithm can end up being a lot slower than even the serial code. And so this is why we kind of have to get out of this this one-by-one serial mindset, and why collective communication really represents true parallelization. In this case, a broadcast would only take about 10 operations. Scattering would be about 10. Scattering both would be about 20 total. Then each process would again only have one element of each vector. And so that would only be one operation again. And then to reduce the result, that would only be 10. So here, this total is 41, and we can see using collective communication, we've achieved the same thing, but in about less than 1/10 of the time of the serial code, and much even more so than the point-to-point equivalent. And so, not to bash point-to-point communication, there's a lot of times where it's extremely necessary, and it's part of your code. In those cases, you're going to be using point-to-point communication, but each process is going to be sending in a different way. Each process is going to be sending different things, and you can create all sorts of crazy topologies where your processes are organized in grids, and so each processes are sending in different directions on these grids, and they're on different communicators. And we'll talk about that briefly, I think, on Friday. But this just illustrates why collective communication is so important. Are there any questions? Okay. And then just a final word about broadcast and reduce. Broadcast and reduce and all these other collective operations are synchronous operations. They work in sync. And so when you call a broadcast, every process has to call the broadcast because it's collective. And so when one process hits a broadcast in your code, it has to wait until all of the other processes also come to the corresponding broadcast. And so all of your code is going to, in essence, sync up at that one point for a second, and then they'll start again. Reduce is the same way. Scatter and gather, they're collective synchronous operations. There is a function in MPI called a barrier, which can be used, which also does the same thing, except its only operation is to make all the processes wait until it reaches a certain point, and then they'll all move on. That's going to be important for timing our codes. But we'll talk about that on Friday. So for today, then, it looks like the assignment is just going to be to complete these 5 exercises here, and it shouldn't be too much. And that's it. All right, thanks.